So, thanks for being here. Thanks for the invitation. I'll talk today about black holes and scalar fields. And that's going to be a complete change of gear with respect to Leonardo's talk. I'm going to start by telling you 3 good reasons why this is an interesting topic, historically. This has been an interesting topic. So, of course, we consider black holes to be quite interesting solutions of general relativity. So, people want to understand their structure. And we have, we know that in Einstein-Maxwell theory, there are uniqueness theorem that says that Kerr-Newman is the unique black hole solution. So, people then got interested in adding more fields to that, and that led to theorems about scalar no hair, essentially, for black holes, which I'll talk about. On top of that, recently, of course, there's been a lot of interest in alternative theories of gravity. So one would like to understand the structure of black holes in theories other than general relativity, and a lot of these theories, as you all know, include scalar degrees of freedom. So potentially you could actually think of using these black holes eventually to constrain theories of gravity, because if their solutions differ from the ones of general relativity, then you could look at astrophysical black holes, see how they differ, and try to impose constraints. And finally, black holes could actually help us learn things about scalar fields themselves. So we could think of that if a scalar field has a significant effect on the structure of a black hole, or it has phenomena that take place in the vicinity of the black hole that are not present in general relativity, we could actually use black holes as laboratories that would help us detect scalar fields and verify their existence. So this is the sort of motivation that one starts with when thinking about scalar fields and black hole spacetimes. And the easiest example you can think of is take a massless scalar field that satisfies this equation here, and assume that it lives in a curved background of a black hole. So this is the basis of Hawking's no-hair theorem. So if you take this equation and you assume that the spacetime you're talking about is stationary, which physically you could interpret as being the end point of gravitational collapse, and asymptotically flat in the sense of being isolated and not receiving anything from infinity, then you can prove that the only solution of this equation is a trivial one where phi is a constant. And this is, in a sense, the proof is actually very simple. It's just 2 lines. You have prescribed the behavior of the scalar field asymptotically by asking it to respect asymptotic flatness, and you're prescribing also actually its behavior on the horizon, because you're asking to respect the symmetries, and that uniquely specifies the solution. And this can actually be generalized to scalar fields with a potential, and the non-trivial part of the generalization is that the solution, the constant scalar solution, turns out to be again the only solution, provided that the second derivative of the scalar is everywhere positive, which you could interpret as a local stability condition, essentially, so that the solution at every point is stable against more scalar perturbations. And this is essentially in one slide the state of the no-hair theorem. And this is in a very, as I said, so far I haven't talked about gravity at all. It's just about a scalar field that lives in a black hole background, except. Yeah.
This stability condition is for any value, or only at the value of infinity?
No, it's everywhere. It has hole everywhere. It has hole everywhere. So it has hole locally at every point. So, excuse me, my voice is a little bit. So, what I was saying is, this is just for a scalar field in a black hole background. Thanks. But the good news is, of course, that if you have what we call a standard scalar tensor theory, so an action with a scalar field non-minimally coupled to gravity and a non-trivial a non-canonical kinetic terminal potential, then you know that you can go to the Einstein frame where it just looks like a minimally coupled scalar field with Einstein gravity and a non-minimal coupling to matter. So if you throw away the matter because you're looking at a vacuum space-time as a black hole, then essentially this scalar field will satisfy exactly the equation I wrote before. So you can look at this equation, you can make exactly the same arguments, you can say that the scalar will be constant, you can plug it in to Einstein's equations, and you're going to get essentially, you're going to get general relativity back in. So the theorems I just said apply to the more general class of standard scalar tensor theories. Is that the end of the story? You have theorems like that, which you could call elegant in a sort of mathematical sense, but does that really tell you that there is nothing we can learn about scalar fields around black holes? They're just like GR, so I have the Kerr solution or the Kerr-Newman if I add a Maxwell field, and things are just boring. And the answer is, of course, no, because even when you trust these theorems, the perturbations, first of all, of these black holes will be different than the ones in GR, right? You have more degrees of freedom, there's going to be scalar excitations you don't have, and that could lead to quite interesting phenomenology. So there's been a lot of active research in these fields, and you can get even things like smoking gun effects, specific effects which you don't have in general relativity. You don't even have for minimally coupled scalar field around the Kerr geometry, but you have for scalar tensor theory. A typical example is the sort of floating orbits found by Cardozo et al., where you have a test particle, it orbits a Kerr black hole in scalar tensor theory, and if you can find that there are special orbits where as it orbits, instead of actually losing energy to gravitational waves and slowly plunging in the black hole, because of superradiance, it mines energy of the black hole, it radiates it away to infinity, and it's actually staying at the same orbit, which is something you could not do in general relativity. So this type of phenomena could be phenomena that you could think of using to distinguish Kerr black holes in general relativity from Kerr black holes in another in a scalar tensor theory. Then, of course, every theorem is as good as its assumptions. So in Noether theorems, the basic assumptions was stationarity and asymptotic flatness. So black holes are not really stationary, neither are they asymptotically flat. They're actually in an FRW background, so the boundary conditions essentially slowly change with cosmic evolution. And indeed, once you take that into account, there is scalar hair induced by the cosmic evolution. And that has been known for some 15 years or more now. Of course, the issue with this hair is that if you do a more detailed study and you try to quantitatively see how much a black hole with this hair differs from a Kerr black hole, the deviation is very, very small. And you can see why, because there are two characteristic timescales in the system: the time scale of the black hole, practically, and the cosmic time scale. And the ratio is a very, very small number, and it's exactly what suppresses this hair. So this type of hair exists, but they're probably not phenomenologically interesting. The other thing you could do is you could go outside the realm of the real scalar field that I said before. You could consider complex scalar fields, and you could think of relaxing the symmetries of the scalar field. So again, the assumption that comes into the theory is that a black hole is stationary and that the scalar field respects the symmetry. So it has vanishing Lie derivative with respect to the Killing, right? That doesn't necessarily have to happen. Consider a very simple case of a real scalar field that has Schiff symmetry, so it participates in the equation only with its derivative. That means that its derivative would be time independent in the usual coordinates without the scalar field being time independent, actually. And that would lead to a whole new class of solutions, and such solutions have been found for instance, by Heredero and Raidu, as I said in this case, for a complex scalar field. So whether these solutions are interesting or not is an open problem for discussion. Of course, perhaps the most phenomenologically interesting thing in all that is the following. This is an equation that most of you will recognize, so it's an equation for the scalar field in the Einstein frame. So there's a standard box operator, potential term, and here is the coupling to matter if there is some matter, right? So if I don't have any matter, then that's fine, then I go back to the equation I had before and I prove whatever I could prove. But the moment I turn on matter, phi equal constant is not a solution of this equation unless these conditions are satisfied for this constant simultaneously. So I'm at the minimum of the potential, right? And at the same time, this function A prime of phi has to vanish. And clearly that's not generically true for any theory I can imagine, only for a subset of theories. So for a generic scalar tensor theory, the moment I add a little bit of matter in there, I'll definitely have to scalarize the black hole. So imagine I take a black hole, I dress it with an accretion disk, phi cannot be constant everywhere. So somehow this will have to induce some scalar charge to the black hole. I put it in the galaxy, again, it will have to induce some scalar charge to the black hole. Now, how big this charge is, it depends. It will depend on the theory and the matter configuration and so on, and it's something that one needs to calculate. And it's not something that has been looked at significantly. So that's another interesting problem. In fact, one thing we did together with Vitor Cardoso, Isabella Carlucci, and Paolo Panni is we actually looked at these specific theories, which is in a sense the best you can do in terms of accommodating the Kerr black hole. So this is a very interesting class of theories, of course. These are the kind of theories that where Kerr could be a solution even in the presence of matter. So you can assume that you start with a Kerr solution, you dress it up with some matter, and then you try to study perturbations around that.
What kind of matter do you have in mind?
As I said, it could be, I mean, generically I would have the accretion disk or the galaxy of an AGN in my mind. Or
So cosmological and then
the cosmological constant, no. The ADS, it depends on the sign actually. Right, so if your solutions of ADS asymptotics, then it's been known for quite some time actually that if you have ADS asymptotics, you can support Kerr solutions with the right conditions on the boundary and so on and so forth. If it's DS, no. And I can actually tell you why in simple words. When I looked at this equation box phi equals 0 vacuum, I said, oh, asymptotically I impose asymptotic flatness that fixes phi there. On the horizon, it has vanishing Lie derivative, and I have the generator there, so I sort of know what the boundary condition is there, and that fixes the solution. Now, if I have de Sitter asymptotics, I have de Sitter horizon, and the same statement holds for the de Sitter horizon. So you've trapped it between two horizons, and you can again prove uniqueness. Okay. So I was saying that if I take a Kerr black hole and I dress it up with some matter, what we showed here is that the scalar field, even if you assume it to be massless initially, even if you set the potential to 0 initially, it actually acquires an effective mass by the coupling to matter. And this effective mass can actually be negative, in which case it develops a tachyonic instability, and it is driven away from the solution, and it actually prefers to develop a configuration. Right? And this is an effect that is already known actually in these theories, but not for black holes, for stars. So, and it's known for stars as spontaneous scalarization. So you take a star, like the sun, and the Schwarzschild solution is a solution of the theory, and actually it is the preferred solution for these stars, but suddenly you start increasing the density of the central density of the star, and you can start consistent solutions, and you see that once you cross a certain threshold in compactness practically of the star, that's the real parameter that plays the role. At some point, the scalar field prefers to develop a configuration. And at the level of perturbation analysis, for a certain level of compactness, the effective mass turns negative, and you see that as a tachyonic instability. And there was a lot of hype with this series, but back in the mid-90s, because back then Damour and Esposto Fares showed that they exist, and the interesting part of it is that they could actually satisfy solar system observations, but still they gave different predictions for neutron stars, essentially compact stars than general relativity, right? So what we saw here is that that is actually an effect that can happen for a black hole as well, as long as you dress it up with some amount of matter. How important it is astrophysically, I don't know, because we didn't with idealized other configurations where we could solve first equations easily, but it's definitely something interesting to look at. What happens when the mass is positive? What happens when the mass is positive is you could actually have superradiant instabilities if the black hole is spinning. So that's another interesting set of phenomena, but I'm not going to talk about it much. Now, so far I talked about standard scalar tensor theories where the theorems apply. You could, of course, decide to deviate from standard scalar tensor theory and consider more complicated scalar tensor theories, which most of you seem to like. So we know already that once you go out of this framework, you can get scalar black holes with scalar hair. And in a paper by Gaddi and Dahl already in 1996, it was shown that if you take Einstein-Hilbert action with a minimally coupled scalar field, and you add this coupling here, where you have an exponential coupling with the Gauss-Born network, you find black holes with scalar hair. So we already know by this example that, and others actually, that once you go outside the framework of scalar tensor theory, you cannot always formulate a an O'Hare theory. There are the already known cases where black holes have scalar hair. Much more recently, there was a paper by Nicolis and by Nicolis on symmetric Galileans, so symmetric generalized Galilean symmetric Hodensky theory, so a subclass of Hodensky that scalar fields do not actually have hair. So you all know what Hodensky theory is so far, but if you didn't, you already know from the other talks. So the shift symmetric version is essentially this action where you've killed the dependence on phi on these functions, g3 to g phi. This x denotes differentiation with respect to the argument, which x is for me the standard canonical kinetic term for the scalar. So this is the shift symmetric Galilean action, and the claim by William Nicolis is that this action does not have any scalar hair for black holes, right? Now, the argument, the theorem or argument is less general a priori than the previous ones, because it assumes spherical symmetry and it goes down to the level of the field equations, whereas the other ones were essentially, if you want more mathematical arguments, we're just assuming stationarity and asymptotic flatness, so much less symmetry, and the proof was somewhat more elegant. The way the proof goes by William Nicolis is actually a very clever proof. So, because of shift symmetry, the equation for the scalar can actually be written as a conservation of the current, the net current of that symmetry. So J mu for me is the current. So assume that you have a line element like this, which is essentially one of the ways you could write the most general spherical symmetric ansatz. This is how they prefer to write it. What they said is, so if I look at the current, staticity and spherical symmetry have to imply that J rho is the only non-zero component of the current, essentially. Otherwise, I would either have a preferred direction in time, or I would violate spherical symmetry. That's nice because it essentially allows you to turn this equation into an ODE. Right? Then the point is, if you go and take the square of the current and you see how it behaves on the horizon, you see that, that J squared is J rho squared over F, and F is the norm of the killing vector that is time like at infinity, which actually means that it vanishes on the horizon, and that would make J squared diverge. So if you want J squared to be finite, that gives you essentially a condition for J rho on the horizon. J rho has to vanish on the horizon. And so that sort of gives you your boundary condition there. And then, because this is now turned into an ODE, you can just trivially integrate it, use this condition, and say that J rho has to vanish everywhere. So far, so good. You've shown that the current has to vanish. The only non-vanishing component has to vanish as well. But of course, there is an extra step involved, because the fact that the current vanishes doesn't automatically say that phi is a constant. Right? Now you have to discuss how the current can be written in terms of phi and its derivatives. And their argument is that J rho takes this form where there is f, there is the derivative of phi, and the first derivative of phi, and then a functional actually of the derivatives of phi, the metric, and first and second derivative of the metric. So the claim is J rho has to have this general form, and if we want weak field theory essentially to be valid and recover the standard term at infinity, which would be just box phi equals 0 plus corrections, then this f has to asymptote to a non-zero constant asymptotically. And if this is the case, since f is a non-zero constant asymptotically, and J rho has to vanish everywhere, and f is 1 asymptotically, that means that the gradient of phi vanishes asymptotically, but J rho vanishes everywhere, so take a small step epsilon inside. Capital F is not going to turn 0 on you just because you took a small step inwards, which actually means that since J rho has to vanish everywhere, by continuity, the gradient of phi needs to keep being 0 as you leave infinity. That is the argument essentially, and that means that J rho equals 0 implies the gradient of phi being 0. So that, and then again, if phi is a constant everywhere, you plug it in the equations, and what you are left with is practically Einstein's equations. So the corresponding black hole would be Schwarzschild black hole. Now, is this assumption really well justified in all cases? And my claim is that it isn't. It's not always true, and we've looked into that together with Sang-Yeon Cho. And so take the metric in this form just because it's more convenient. Again, it's a spherical symmetric metric, but now written in terms of the aerial radius coordinate, the usual r. Right? And you can just write down the current, first of all. So that ugly. So it's this one here where r and s are just the components of the metric, and the primes denote differentiation with respect to the r coordinate. And what you see is that by inspection, they seem to be perfectly right. I mean, there is f prime, f prime square, f prime cube, and so on and so forth. So you can always peel off an f prime factor, and then have the rest. And the loophole comes into the fact that, of course, these things here are functions of x, and x is f prime squared in this case. So what kind of functions of x are they? Are they all analytic functions at f prime equals 0, at f prime equals 0, for instance? And there's actually two ways to violate the assumptions they've done. One is, of course, you could have g's that go like 1 over f prime to some power, the power being high enough that you create a pole when f prime goes to 0. So f cannot really be a constant because that would make the current diverge, right? But that is not really sort of a sensible criticism, of course, to whatever they're doing, because that would be a theory where f cannot be a constant, so the theory doesn't really admit Lorentz symmetric vacuum somehow. F would always have to have a non-trivial configuration and so on. These theories do exist, such theories do exist within the Hordensian class, but clearly they're not the theories they had in mind. However, there is also the possibility that one of these g's scales in exactly the right way, so that one of the terms becomes phi prime independent in this current. And that would actually violate their answers. And this is exactly the loophole. So instead of actually reconstructing it back from the current, you can go a little bit more general. It's actually easier. So you could say, what do I want? I just said that I want the current to have a term that is independent of phi. That means actually that the equation should have a term that is independent of phi, right? So the action needs to have a term which is linear in phi. So that when I vary with respect to phi, phi just disappears, right? So let me call it phi times some function of g. Now, I have shift symmetry here, so that restricts severely the form of A of g, right? Because the only way I can have shift symmetry and afford to have a term like that in the action is if A is a total derivative. So A has to be a total derivative, and at the same time, of course, this is Hordensian theory, so whatever this variation is, it has to lead to something that is second order in derivatives at the end of the day. And essentially that singles out a unique choice. A can be the Gauss-Bonnet invariant, which is very similar to what I showed you before, but now instead of having an exponential coupling with phi, I have a linear one. And that satisfies shift symmetry. So the simplest theory you could imagine is this one. So R plus standard kinetic term plus linear coupling between phi and g. You vary with respect to phi, you get this equation here, right? The Gauss-Bonnet invariant vanishes only for flat space-time because it contains the Boltzmann scalar. So in any other solution, phi cannot be a constant. That is clear. So there is no chance that this theory has black holes, which do not have hair. And this is clearly a theory within the Hordensian class. This term should not throw you off. It can actually be written in a conventional way, and that's already known. It's in the paper by Yassi et al. How to choose G3, G4, and G5 to reproduce this action. Okay, so that is the one term you could write down that circumvents the argument by we and Nicholas. And of course, in general, you have no reason to not have this term. There is no symmetry that protects you with respect to the other terms. If you just want to set this one to 0, so there's I can't think of an argument to say that, okay, I just set the coefficient to 0 and that's a technically natural choice. So I do think that it compromises the generality of the theorem. You could certainly cook up a symmetry that would do away with this term. The easiest one I can think of is reflection symmetry, phi going to minus phi. But of course it doesn't kill just this term, kill a whole bunch of it. So if you were to impose this symmetry, you would end up with this action here. And this certainly has only GR black holes, right? So for this, certainly the theorem applies, and it looks like a sensible theorem. On the flip side, you might be worrying about the fact that this theorem is just a theorem for spherically symmetric black holes. Actually, Noether theorems about spherically symmetric black holes when it comes to scalar fields are more powerful than they seem. And the reason is that suppose that you have this spherically symmetric black hole, which is a GR black hole, and now suppose that you want to turn it to make it rotate, but rotate slowly. So you want to go in an approximation where your black hole is rotating, but it's not rotating very fast. Then you want to generalize your symmetry to stationarity and axisymmetry. And there is a well-defined notion in which, in general, and well-defined procedure in which, in general relativity, we obtain slowly rotating black holes from slowly rotating solutions from spherical solutions developed by Hartle and Thorne. And the basic physics behind it is you're saying, look, if I have a physical system which is rotating, I don't expect actually that if I flip the direction of rotation and I change the sign of my phi coordinate or my t coordinate, that changes anything in the system, because that's exactly how I define the rotation. And so that actually tells you, when you make an ansatz, what terms could depend on the rotation to linear order, what terms could depend on the rotation to quadratic order, and so on and so forth. And so if you want to order, essentially, the corrections to the scalar by order in the rotation, you can argue that the scalar cannot receive any linear correction in the rotation, because if I would perform the operations I just said, that would actually change the sign of the correction. And therefore you can argue that if spherical black holes have no hair, then their slowly rotating counterparts, at least, will not either. I mean, you could have fastly rotating black holes that do not continuously connect to spherical symmetry and so on and so forth. I mean, that's definitely a possibility that you can exclude, but I think that sort of, it's just there to demonstrate that these spherical symmetric theorems are not as elegant and as powerful as the ones only with stationarity, but still they're quite powerful. Now, the last thing I want to do is, of course, I want to look into the solution, into the black hole solution for the hairy one, and try to understand it a little bit. So, let me go back. So I'm going to work with this action. Clearly, if you take the general Hodensky action and try to find a solution, it will have to look somewhat similar to the one I'm going to find by looking at this action, because this is the unique term that will introduce the hair action. So it's quite interesting to look at the solution for exactly this action, which is of course much simpler than the most general one. So the first thing you could do is you could try to generate a solution perturbatively by starting with Schwarzschild and working perturbatively in this coupling alpha, which is the coefficient in terms of phi Gauss for net. And if you do that, you see that the first order in the coupling, you already get a non-trivial scalar field profile. It's sort of trivial to solve the equations. However, phi prime and hence phi diverge on the horizon, right? And that forces you, if you want to avoid this divergence and have a regular solution on the horizon, that forces you to fix the integration constants appropriately, and that actually fixes the scalar charge asymptotically with respect to the mass. So the solution is hairy, it has a non-trivial black hole configuration, but it doesn't have an independent charge, because regularity fixes the charge with respect to the mass of the black hole. To this order in alpha, the space-time remains Schwarzschild. You have to go one order higher in alpha to take into account the back reaction of phi, and then the metric ceases to be Schwarzschild. The scalar profile remains unchanged, and what I've written here is the ADM mass now of the black hole, which, instead of being just identical to the mass parameter m that I had before, now receives some contribution from the scalar charge, which remains fixed with respect to the mass. Okay? So this is the perturbative part of the solution. One question one could ask me at this stage is, should I be going higher and higher orders in perturbation theory? And is this all there is to it? And that really depends on where you think you got this theory from. Right? So when I write down this theory, one has to tell me what alpha is. Is alpha a perturbative parameter that some bookkeeping parameter that, and I expect to have here 3 dots with order a squared and order a to the cube, higher order correction. If yes, then I should have stopped at first order in alpha and say, look, I didn't take into account a squared corrections in the action, so I can't consider a squared corrections to the solution because that doesn't make any sense. If instead I want to treat this theory as exact, where alpha is just some coupling, and I'm just looking at the small coupling limit in a way of generating perturbatively the solution, then of course I could go to higher orders in alpha, or I could do a full numerical analysis and get a solution which is valid at all orders in alpha. And that's what comes next. So if I go and generate a numerical solution, which is exact, then you see, of course, all of the characteristics I already discussed so far remain. The scalar charge is fixed, but what you see here, you see the value of the scalar field as a function of R, and the value of the Gauss-Bonnet invariant as a function of R, and you see that they actually diverge at the finite radius. So that's before my solution was Schwarzschild, and even at order a squared, where you had the correction, you still had a central singularity at R equals 0. I didn't show you that, but this is the case. Here, in the numerical solution, you get a finite area singularity at a finite value of R. So already at this level, you see that the perturbative solution and the non-perturbative one do not agree. They agree outside very well, but not as you approach this, this radius. So that's quite an interesting characteristic because it essentially means that black holes have a minimum size. So what you see here is the singularity radius, this finite area singularity radius, as a function of the coupling scaled by the radius of the horizon, right? And you see that it increases, it increases, it increases, and essentially at some point it reaches the horizon of a black hole of a given size, right? So from then on you can have a black hole, right? If the horizon meets the singularity. And that's quite an interesting feature of these solutions. It was actually already there in the solution by Caddy et al. And so that's the red line. What is the dotted line that you see closely tracing this is actually the characteristic radius that if I take the perturbative solution I looked at before, and I look at when the order A, the order alpha correction becomes of the same size of the order alpha squared, and I plot that, that's the dotted line. So you see why in the perturbative solution I don't actually see this feature, because it goes beyond the range of the validity of the perturbation scheme that I have. Okay. So, and that's just something about observables. So you could of course wonder how much does the solution differ from the Schwarzschild solution, and the truth, very little. The answer is very, very little. So here are two things you could consider as observables. On the left panel you have what is called the gravitational radius minus the horizon radius over the horizon radius. So essentially the fractional deviation. The gravitational radius is just the Schwarzschild radius associated with the ADM mass. So in GR that would be 0, obviously, because the Schwarzschild radius and the horizon radius are the same. Here they can differ, but the deviation, as you see, this is a logarithmic plot. It's very, very small for different values of alpha. And this is essentially the this is just a check between the numerical and the perturbative solution of the radius of the innermost stable circular orbit.
Do you have a plot of the listener submass?
Sorry?
Do you have a plot of listener submass? The case I was from the Hawking mass?
No.
So that, I mean, so from where do you have a main contribution to the mass?
You have both from the whatever is the mass parameter of the black hole and the scalar charge.
The function R. The function R.
Oh, I don't know. I have not thought about it actually. Yeah, I don't know about that. But why do you think that is important?
Because I want to see how singularity appears as a vehicle. And so if the Mr. Submass becomes negative at some point, then maybe we have singularity like singularity of the negative mass.
I would guess not. I mean, in general, I mean, the finite area singularity is of course well within. I mean, for large enough black holes, it's well within the horizon radius, and the profile decays of the scalar decays fast enough, which is what contributes extra to the ideal mass.
So the energy position is always
Yeah. So that's just the issue between the numerical and the perturbative solution, just to show you also that the numerical and the perturbative solution agree very well until you actually reach a size where you're very close to where the horizon sits very close to the finite area singularity. Right. So with this, let me conclude. So what the point I try to make here is that no-hair theorems are, of course, interesting and a good starting point. Sometimes, I mean, they're quite important in the sense that sometimes they're what justifies to just do perturbation theory around the GR black holes instead of going and looking for other black holes which might be far more complicated. So in this respect, they're very helpful, but they're not the end of the story, because even in simple scalar tensor theory or theories where we can prove no-hair theorems, phenomenology, scalar field phenomenology around them can be very different, and once you include matter in the game, or cosmic evolution, or relaxed symmetries, you might actually get scalar configurations around your black hole. So that's definitely a promising avenue in detecting scalar fields and checking deviation of general relativity. Black holes, solutions with non-trivial scalar profiles exist and are quite interesting solution. I think that the solution I showed is an interesting solution in general. And they can have novel features. And I think black holes are going to be the next frontier in detecting deviations of general relativity and the existence of scalar fields. So that's all. Thanks a lot.